In this video, I'm going to introduce rational functions, graph several simple rational functions, cover some rules for finding asymptotes, and then I'm going to cover a really nice method for graphing rational functions. First, we'll cover what is a rational function. Well, the word rational has the word ratio in it. A rational function is a ratio of polynomials, where the denominator has a degree of 1 or more. And here's some examples and non-examples. F of x equals x squared over x minus 1 is a ratio of polynomials and the degree of the denominator is 1 or more. F of x equals the square root of x over x minus 1 is not a rational function because square root of x is not a polynomial. F of x equals 1 over x squared minus 1 is a rational function. You might think 1 is not a polynomial, but actually it is. It's a 0-degree polynomial. And the last example of f of x equal x squared minus x minus 1 over 3 is not a rational function because the denominator is 3, which has a degree of 0. And in fact, the last example is the same as 1/3 x squared minus 1/3 x minus 1/3. So it's really just a quadratic function. A rational function is said to be in reduced form if there are no common factors that may be canceled. Here is an example. F of x equal x squared minus 1 over x plus 1. The numerator factors as x plus 1 times x minus 1, and the x plus 1's cancel out, leaving x minus 1 with the condition that x is not equal to negative 1. This is a tricky function to work with. In fact, it's something we deal with in calculus class. It has what's called a discontinuity at negative 1. For this class, we will only work with rational functions that are already in reduced form. So you really don't have to worry about this. All your functions you see will be in reduced form. And we're going to start things off here by graphing about the simplest rational function you could work with, and that's y equal 1 over x. And we're going to plot this by plotting the points I have given here in the table. And we have quite a variety of positive and negative x values plugged in here. Everything from 1/10 up to positive 10. You can see in the graph we have 1, 1 plotted, 2, 1/2 plotted, 4, 1/4, 10, 1/10, which is almost on the x-axis, 1/2, 2, and then 1/10, 10. And then you notice when we put in the negative of those x values, we get the negative of the y value because this is an odd function. And that means we have symmetry with respect to the origin, so that even odd business we learned about with function graphs is helpful here. So we have all those negative x values plotted, and you can see it's a rotation about the origin. And notice that when we plug in x equals 0, we get 1 divided by 0, which is undefined. What that means is we have no points of this graph that cross the y-axis. So I put this big red line through here. It's a boundary. It splits the graph in two parts. If you were to cross that line with a point, that would mean x would take on the value 0, which would give you an undefined value. So no points can cross that big red line. And notice what this graph does. As we get close to that y-axis, the red line, x equals 0, the graph just goes down to infinity. Also, on the left side, the graph gets closer and closer to the x-axis. And on the right side, the graph shoots straight up to infinity, levels off to the x-axis on the right. We say that y equals 0 is a horizontal asymptote. And the horizontal asymptote is a horizontal line that the graph levels out to as you plug in very, very big x values. Likewise, since the graph approaches the vertical line, which is the y-axis, also known as the line x equals 0, we call x equals 0 a vertical asymptote. Asymptote means boundary. These are boundary lines for the graph. Now we're going to do another graph that has a slightly different vertical asymptote and horizontal asymptote. In this next example, we're going to graph y equal 2x over x minus 2 by plotting the given points, and then when we're done, we're going to indicate what all the asymptotes are. So we have all these points. We plug in negative 10, you get negative 20 over negative 12, which is 20/12, which is this point right here. When x is negative 1, we get 2/3. When x is 0, we get 0. When x is 1, we get 2 over negative 1, which is negative 2, this point. When x is 1.5, we get 3 over negative a half, which simplifies to negative 6. That's this point down here. And we plug in all the other points, and I have them plotted here. 2.5, 10, 3, 6, 5, 10/3 or 3 1/3, and then 10 gives us 20/8. And then we look at the graph and see, where does it level out to? Well, to me, it seems to level out to y equals 2. And also, vertically, it seems to take off up and down near the vertical line x equals 2, which is right here. To verify this, I plugged in some really large positive and negative x values. When x is 200, the y value simplifies to 2.04. The graph is approaching that green line y equal 2 from the top, getting closer and closer to 2. When I plugged in negative 1000, I get 1.996. The graph is approaching the green line y equal 2 from below, getting closer and closer to 2 in value. Also, I plugged in a couple x values very close to the red line. That's our vertical asymptote. When I plugged in 1.99, I got negative 398 for the y value. That graph is taking off downward faster and faster on the left side of the red line. But on the right side of the line, when x is 2.01, the graph is taking off in a positive direction, up toward infinity. So this confirms that the vertical asymptote is x equal 2 and the horizontal asymptote is y equal 2. But I note, it is far easier if you find and plot the asymptotes first and then finish off your graph. You don't need 12 or 15 points. You really only need about 4 points if you get those asymptotes first. So we're going to cover methods of finding the asymptotes. First, I'm going to go over the definitions again. The vertical asymptotes are the lines where the graph takes off to plus or minus infinity near division by 0 x values. The horizontal asymptotes, and there's only going to be one per graph, is the line that the graph levels off horizontally to, out on the edges, when x is a large positive or negative value. And here I have the rules for finding the asymptotes. As we have seen, vertical asymptotes in reduced functions occur at values of x resulting in division by 0. So just remember division by 0. And because we get division by 0, that forms a vertical boundary. The graph cannot cross that line. The example here is y equal 1 over x minus 2. X equal 2 causes division by 0, so the vertical asymptote is x equal 2. Now for horizontal asymptotes, we have two rules. The first graph we did was 1 over x. That had a horizontal asymptote of y equals 0. Well, it turns out that whenever the degree of the denominator is larger than the degree of the numerator, you get a horizontal asymptote of y equals 0. That's because the denominator is getting bigger much faster than the numerator, and the result is closing in on 0. So then the graph is going to level out to y equals 0. And here's an example where f of x equal x squared minus 1 over x cubed plus 2x. X squared minus 1 has a degree of 2. X cubed plus 2x has a degree of 3. This graph will have a horizontal asymptote of y equals 0. Now in the second graph, we had a horizontal asymptote that was not 0. It turns out the horizontal asymptote will always be y equal a over b if the degrees are equal. A is the leading coefficient of the numerator, and b is the leading coefficient of the denominator. And here's an example. F of x equal 4x squared minus 1 over 5x squared plus 2x. The degrees are equal. They're both quadratics. So we take the ratio of the leading coefficients 4 over 5, and we get y equals 4/5. That's our horizontal asymptote. And this rule works because when the degrees are equal, the numerator and denominator are growing at the same speed. So you're not getting a ratio that's heading towards 0 as the denominator gets bigger than the numerator. Here they get bigger at the same speed. It's only those leading coefficients that tell you what the graph is approaching. And there's also a rule for a slant asymptote. We're not going to cover that right now. The slant asymptote occurs when the degree of the numerator is 1 greater than the degree of the denominator. At any rate, now we have a nice method for graphing. And here's the method for graphing. Find and plot all the asymptotes. Number 2, find and plot several points on each side of each vertical asymptote. And number 3, complete the graph using your knowledge of the behavior of the graph near the asymptotes. And you'll see how easy this is with the following example. We're going to graph y equal x over 2x plus 6. Well, the first asymptote defined is the vertical asymptote because it's easy to find. The vertical asymptote will occur at values of x that result in division by 0. Here, 2x plus 6 equals 0 when x is negative 3. So the vertical asymptote is x equals negative 3. Now here the degrees are equal of the numerator and denominator. They're both first degree polynomials. So we use that second rule for horizontal asymptotes where we take the ratio of the coefficients. Y equal x over 2x plus 6 is the same as y equal 1x over 2x plus 6. The coefficients are 1 and 2 and the ratio is 1 over 2. So y equal 1/2 is our horizontal asymptote. X equal negative 3 is our vertical asymptote. Now let's plot them. Okay, I've plotted the line x equal negative 3, this vertical line right here. And I've plotted the line y equal 1/2, which is this horizontal line right here. And now we find some more points. And I only have 4 points here. When x is negative 4, y is negative 4 over negative 2, which is positive 2. And that's this point right here. When x is negative 6, we have negative 6 over negative 6, which is positive 1, which is this point right here. And when x is 0, y is 0. That's easy enough, right at the origin. And then when x is negative 2, y is negative 2 over positive 2, which is negative 1. And that's this point right here. Now we just draw a curve through these points. And I'll do my best here with my graphics that I have. Just connecting up these 2 points on the left, we see that the graph is trending up towards the vertical line. That means it's going to continue trending up to positive infinity. It's leveling out from above on the line y equal 1/2, and it's going to continue to level down to that line. On the right side of x equal negative 3, we just have these 2 points. And if I connect them up, we see that the graph is trending up and it's leveling out to that horizontal line y equal 1/2. And on the right side of the vertical asymptote, it's heading down. Just these 4 points were enough to give me the graph, and that's very, very close to the actual graph, what I have plotted right here. And there are variations of rational functions, so I've graphed some more examples on additional videos. There's 2 additional videos that follow this that go over graphs of rational functions with multiple vertical asymptotes and other types of rational functions. So make sure and watch those as well.